Welcome to Lesson 14, Converting Rational Numbers to Decimals Using Long Division. For this lesson, I'd like you to have a calculator handy. Alrighty, so I'm going to ask you a question here. In the last lesson, we used powers of 10, powers of 2, powers of 5 to find equivalent decimals for certain fractions. Okay, now we're going to do something different. So for example, and we talked about this already a little bit, but for example, if we have 1/6, is it possible to use factors of 2 or 5 in the denominator to go ahead and turn this into a decimal? So if we look closely, we'll see that there is no easy way to do that. The only factors of 6 we have are pretty much 2 and 3 and 1 and 6. So 2 times 3 is not going to help us at all. Okay, so we have to find a different way, and the way to actually turn a fraction into a decimal, and I know many of you, hopefully most of you, understand the way. Is to take your numerator, okay, and divide it by your denominator, because that's exactly what fractions are. Fractions are division. They are another way to actually express division. 1 divided by 6 is the same as 1/6 or 1/6, because that says 1 divided by 6. All right. So we can actually use our calculators to find decimal equivalents for all kinds of fractions. All right, so what I want you to do, this next activity right here, one that's probably makes everyone happy here, is that we're going to use our calculator. So what I'd like you to do is just go ahead and pause the presentation and go ahead and using the integers, just use the integers 1 through 20, okay? Go ahead and explore some division, and go ahead and write the fraction representation down here, and then the corresponding decimal representation right next to it. Okay, so for example, if I were going to go ahead and take the, I'll do a real simple one. Most of us know this, but actually I won't use that one because that's too easy. But how about 1/8? Okay. Now 1/8, of course, what I'm doing here is I'm dividing. What I'm doing in my calculator, I'm going 1 divided by 8. Okay, and then equals, and what I come up with for 1 divided by 8 is 0.125, and this is what's going to appear on your calculator screen. Now, some of these are going to get really weird, because if you look at 1/9, for example, you'll come up with something that looks like this: 0.111111. It'll just fill in your calculator screen with ones until it can go no further. All right. As you see, with 1 divided by 8, it is indeed a terminating decimal. It ends. Now, 0.111111 is a repeating decimal, which is fine, and it qualifies as a rational number. We talked about that earlier when we talked about rational numbers. And it could be written very simply like this. You just need two ones, and then the line on top of it, which tells you that it repeats forever and ever. Okay, but the fact that it repeats is qualifies it as a rational number. Okay, so go ahead and do that. Just write some fractions and their equivalent decimals in this space. So go ahead and do that. Okay, so you've probably come up with a couple of different scenarios here. Now, this question B here asks, what 2 types of decimals do you see? Which might be a very strange question to you, and kind of was to me when I first looked at it. But the 2 different types of decimals are those such as here, 1 divided by 8, which yields you a 0.125, a terminating decimal. You know, of course, 1/2 would do the same because that's 0.5 terminating. It ends. Okay, but then the other one would be like 1/9. 1/9, 1/9 divides out to look like this, just a series of ones. So it repeats. But there are some that are like 1/7 over here. Now the problem with this one is that sometimes you get a calculator screen that does not hold as many digits. Okay, so in this case, 1, 2, 3, 4, 6, 7, 8, 9, 10 digits here. Sometimes it will be just 8 digits on a calculator screen. Fewer than 10 would actually not reveal the fact that 1/7 actually yields a repeating decimal, because this portion of it repeats. Okay, I should probably put that in red so you can see it, but this portion right here repeats. The 0.142857, you can see it's starting again right here. We'll go in this way, 142.857 will continue. So it repeats there. So this would also qualify as this second type of decimal. Okay, so what two types of decimals we see? We see terminating and repeating. Okay, and any time you make a fraction out of two integers, like all of these are, you are going to get a rational number. Okay, so they're all rational numbers, and they will always follow either a repeating pattern or a terminating pattern. Okay, so in that table, the table on your first page there in your binder, if you would go ahead and just organize those fractions that you made, maybe you made some, maybe you didn't make any, but if you haven't made any yet, go ahead and do so. And then once you come up with several, just go ahead and organize them in this chart based on terminating. You can see those that are terminating on the left-hand side and those that are, we're going to call non-terminating on the right-hand side. So for example, when I did 1 divided by 9, that was, remember that was 1/9, 1 divided by 9 equals 0.11111. Okay, so that was a, I could put ... one over here. That was my one non-terminating. Terminating one, very famous terminating one, of course, is 1/2, 1/2, and that equals 0.5. See, that terminates. Now what I want you to do after you do, let's say do 3 or 4 of each, go ahead and think about these questions, and if you want to write some answers to those. What do these fractions have in common? What do these fractions have in common on this side? So the terminating, what do they have in common over here? And then what do the non-terminating decimals, what do they have in common? Okay, so here are a few that I included here: 1/2, 1/4, and 1/5 on the terminating side, and then 1/9, 1/3, 1/11 on the non-terminating side. Now, the most important part, and again, let's take a look at some of these. You know, just looking at 1/11, for example, I'm very curious. You can see it could also be written just like this. You know, 0.09 with a line over it, because you see that 0.9 continues to repeat. All right. So what do these factors have in common? So let's look on the terminating side. Very interesting. Maybe some of you have made the connection to the last lesson. But if you notice, all of these fractions have factors in the denominator of either 2 or 5. Okay, either 2 or 5. As you can see over here, the denominator is 2. And of course 2 is actually 2 to the first power. 4 is 2 to the second power, 2 squared. And then 5 over here is 5 to the first power. Okay? So all of those have 2 or 5 as common factors. We could even look at 1/8 would qualify as well, because 8 is actually 2 to the third power. Okay? Yeah, so over here now on the non-terminating side, all these factors, they have at least one other factor their denominators have at least one other factor that is different than 2 or 5. Of course, up here, 1/9, that's actually 3 squared, 3 to the first, and 11 to the first power. But yeah, so they have only have will have at least one in there. And again, 1/6 was the same way. And even though 1/6 looks a little different than those, all of these just happen to be, well, actually, I'm sorry, they don't happen to be. They're all odd numbers. That doesn't really mean anything. 5's an odd number as well. But 1/6 is actually 2 times 3. So you do have 2 as one of the factors, but you have something other than 2 or 5, which is a 3 as a factor. Okay, so very, very difficult or nearly impossible to put these non-terminating decimals. They can't end. You can't have them fit into a tenths or hundredths or thousandths. They just go on and on and on. Their end is really, well, there never is no end, which is a very interesting thing in math. Terminating, though, very clear. We have 5/10 here, 25/100 here, 2/10 here. Okay? Okay, so example 3 is about converting rational numbers to decimals using long division. So here comes the long division, again, something a favorite of some of us, and a kind of a bear for some of us. So I'm going to have you do that by yourself and then come back and check out what I did. So let's go ahead and just start with this one. Use the long division algorithm to find the decimal value of -3/4. Okay, so in setting up my division algorithm for a fraction such as this, it's a proper fraction, okay, where you have a numerator that is less than the denominator, okay. I know when I set it up I'm going to need a decimal point because I am talking about a quotient that is going to be less than 1. So I need a decimal point, all right. So when I set it up like this. I have my 4 outside my bracket, and inside I put my 3, and then I have my decimal point and my 0. Okay, I can actually bring that decimal point up to here, okay, in my quotient section, and then just go ahead and do my long division like I always would. And I know there are 0, 4s, and 3. Okay, it's good to have that 0 on that side. So then I'm looking at 30. How many 4s are there in 30? We know that I know that we have 7. Is that there? And again, I'm just going to ignore any kind of decimal points from now on while I'm doing the algorithm because it's really not necessary to bother myself with it because I already have my decimal point drawn up here. So I have an idea. I know where my decimal point goes. Okay. So then 2, bring down 2, and I know that is 5. Okay. So that is my answer. My answer right here is 0.75. Some of you may have known that. 3/4 is also 3/4. 3/4 is 75 cents. Okay, and all of that. But anyway, 0.75. The only thing missing from my answer, of course, is the negative sign because I am writing an equivalent decimal to this fraction, which is negative. Now, it doesn't matter if it were because the truth is, one of these, the numerator or the denominator, is going to be negative. But we know by our integer, division of integer rules, it does not matter whether you divide a positive by a negative or a negative by a positive. We're always going to get a negative when we have different signs being divided or multiplied for that matter. Okay? So there's my answer for that one. All right, so go ahead and do, what do we have, letters A and B. Go ahead and do letters A and B here, and come on back, and I'll just have them done. I don't think I'll go over them step by step, but I'll just have them done for you to check. Okay, well, here are the answers to these two, and I'll actually show you if you wanted to pause and just take a look at my algorithms and see how I did them. And again, you can see I'm paying attention to the fact that I need negatives. Okay, so negative 7/8 as a decimal is negative 0.875. Actually, it's not as negative here, is it? I'm sorry. This is actually 3/16 is actually 0.1875. Alrighty, and you can see the steps I went through. And you notice that every time I have a remainder here, look, when I did this, I took 30 and took away 16. I had 14 was my remainder, then 12 was my remainder, and then 8 was my remainder. These are all different, and that's going to play a part in understanding or being able to identify a repeating decimal early go at that. You can see I had 6 here and then a 4 here, and they were both different. Okay? Okay, so example 4, converting rational numbers to decimals, again using long division, continued. Now we are going to see something new happen, and again I know you know the answer to this, 1/3 as a decimal, but let's just watch and just identify what happens here. Okay, again I have my decimal point here, my 0, decimal point here, 0. Okay, and that's 3 and 9. Okay, so here's my remainder, 1. Okay, so now I got to bring it down 0 again, and I have 3 again, and then I have 9, and I have 1 again, and then I have 0 again. Okay, and that's going to be 3 and 9. So as you can see, my remainder right here, this remainder, I continue to have a remainder of 1, remainder of 1, remainder of 1. If that repeating remainder, if that continues, then you know you're repeating, and it's not going to change here. Okay, there's never going to change. All right, it's not always that simple. It doesn't always happen that it's the same remainder consistently, but we'll see some examples of different ones in the future. So go ahead and how about you go ahead and well, actually, let me just, we talked about this before, but might as well reiterate it now. So if I have this answer, I know it's going to be 0.3333 and so on, right? It's going to continue to repeat. I don't need to write it like that, of course, using my little ellipse here, 1, 2, 3 ellipse. All I need to do is put 0.3 and a little line over the top. Some of you probably knew this already, but that is the part that repeats, okay? It's going to be the 3. The 3 repeats, therefore you need just to write it 3/10 with a line over the top, and that is what designates the fact that that 3 repeats into infinity. Okay? All right, so exercise 2, calculate the decimal values of the fraction below, or fractions below, using long division. So express your answers using the bars over the shortest sequence of repeating digits. Now, in this case, with the 1/3, that shortest sequence was just the 3. Okay, that may differ in these other examples. So go ahead and do that, and come on back, and we'll see what you got. Okay, so here is -4/9. I just realized I forgot my negative sign there. -4/9 works out to, you can see very clearly, the repeated remainder of 4 continues to repeat, and you can see where that stays. So I would write it like this, -0.4 with my bar on top there. Okay, now over here with my 1/11 or -1/11, you can see what happens here. Interesting in the sense that I have actually a 0 remainder. Well, actually 10 remainder here. There's 10. Okay, and then my remainder goes down to 1. All right, and you can see that what happens here. Actually, the first time I try to divide 11 into 10, which looks like this, not necessarily 10, but it's 1. I can't, it doesn't fit. Okay, there are no tenths right there. So then I go down and I end up with a repeated decimal, repeated remainder 10. Then 1 comes up, and then 10 again, and then 1 again. Okay, so these are different sets of 2 different repeating decimals, repeating remainders. And it keeps going 10, 1, 10, 1, and hence the fact that we get a series here of 0, 9, 0, 9, 0, 9, and that answer would be written, again it's negative, so it's negative 0.09, and that's where my bar needs to be over. Again, we're looking to express answers using a bar over the shortest sequence of repeating digits, and the two digits that repeat are 0, 9. Okay, 0, 9, 0, 9, 0, 9. So this is what your answer would look like here. Okay, I didn't have enough room here to do these other two, but I wanted to actually do them because they're quite fun to watch. And we're not talking about 1/3 anymore. We're talking about 1/7 was letter C, and let's just watch this one. Let's watch this one go down. All right, so here we go. 1, then we have 7, okay, 3, and you might be thinking to yourself, okay, 4, this is going to end pretty soon, right? Whoops, no. Oh no, what is this going to be here? That's going to be 2, that's 14, oh, 6, 0, then we've got 8, 56, 4, no, not quite yet. And that's going to be, what, 5, 35. Oh my gosh, look at all these. Oh boy, this is, what is going on here? And then we have 7, 49, and then we have 1. Okay, that looks familiar, that 1. And 7, and 3. Oops, things are happening. Okay, so we get a sense of what is about to happen now. So as soon as this happens, and it happened already, right here, where we saw that we had 1 here, but then we actually have 1 here we're dividing into. But as far as remainders, you see my remainder of 3 here. Here's my remainder of 3. And again, if I have a remainder of 3 after subtracting 1 from 10 right here, I did the exact same thing, or 7 from 10, I'm sorry, 7 from 10 here. I did the exact same thing here, so the pattern is going to repeat. And if we did it, of course, that would be 28, and then there's 2 remainder, 20, and then it would be 2 again. You can see that right here. Okay, so we see it beginning right here, and we talked about this already, actually, beforehand. But so this would actually look like, we're going to write it as an answer. It is a positive one, right? Yes, 0.14287 with the line over the bar over the entire series there. Okay, because that is the shortest sequence of digits that repeats, because then we're going to have that same thing happen all over again. But really, really a lot of fun. Now the 5/6 or 5/6 is actually also another fun one. I'm just going to go ahead and put it over here. Okay, because it does something really interesting. 0. So here's 8, 48, and then 2, 20, and what is that? 3. 18. Oops. Ooh, what a C. Ooh. Good. Got a repeating remainder here. There's my remainder. My remainder was 2 up there. It's 2 again. If I know it's 2 again, I know it's going to happen. I'm going to have 3 again. And 18, of course. This is going to yield another repeating remainder. So my remainder has started to repeat. Therefore, my quotient, the digits in my quotient are going to repeat. But this one is interesting because now it's 0.83. Now the line goes over the 3 only because it is the digit that repeats. The 8 does not repeat, so it would be not correct to do that, because if we wrote the bar over the 8.3, that would mean that my decimal was looking like this. And that may indeed be the case with some fraction, but not with this one. Okay, so be very, very careful when you're doing that, because this is just the 3 that's repeating. Okay? Alrighty. Okay, well, this next question, if you tried to read it yourself, can be pretty daunting to read and try to understand, but let me read it out loud to you and then I can try to explain it. How do we determine, I'm reading right up here, how do we determine whether the decimal representation of a quotient of 2 integers with the divisor not equal to 0 will terminate or repeat? Okay, so what we're looking at here is how to determine whether the decimal representation of a quotient of two integers. So I'm looking at, so for example, 1, let's use one we've used already, 1 over 9, I guess. Let's use 1 over 9. Okay, so 1 over 9. Okay, the quotient of two integers here is just what we're going to do is we're going to do 1 divided by 9, because that's what this means. That's what this fraction means. Okay, so here is our quotient of two integers. What we're doing is we are going to, and again, we've talked about this before, but this is our divisor. Okay, that's the divisor. That's what we are breaking this thing up into, or dividing by. This is our dividend, which correlates to our numerator of our fraction. And then the answer up here, whatever we get here, that's our quotient. Okay, our quotient. So they're asking us here the decimal representation of a quotient. So that's going to happen right up here. That's going to be where our decimal representation of this is going to happen. Okay, so how do we determine whether that will repeat or terminate? How do we determine that? And again, it has to be, with a divisor not equal to 0. And again, you can't have 0 here. That doesn't work. 0 as a denominator or 0 as a divisor. Okay, it's just that is not a rational number. Okay, so how do we determine that? So I'm just going to get rid of all this. I just wanted to explain it with that. The way we would determine it is this. So if we look at, again, 1 divided by 9, I guess that's a good one. Okay, 1 divided by 9. We know if, well, let's look at one that does terminate. And this all just makes sense. So 1 divided by 2. Okay, and 0, 0 there, and that of course is 5. So as soon as I have a remainder of 0, we know it's going to terminate. Okay, we know it's going to terminate. Terminates right there. All right. But well, let's look at the 1/7, which is so much fun. I'll do it over here because it does take. Well, I should probably do it over a little bit further because it does take up a lot of room. Okay, 1 divided by 7. All right. So now I go ahead and do my first. I have 1, my 7, my 3. Okay. Now this remainder here, it can only be, there's only a few possibilities, okay? And it's all based on what this divisor is. So with the divisor of 7, okay, this remainder is only going to be either 1, 2, 3, 4, 5, or 6, okay? That remainder cannot be 7, because if it was 7, I could still get another 7 out of 7. Can't be 8, same example, can't be 9, all right? So it can only be these, okay? So as soon as we see one of these repeat, and actually in this case is going to be the 3, as soon as we see that 3 repeat, we know it's all going to happen again. Okay, and we can watch that happen. Here's 4, 20, and then we had 2, 14, I think I'm doing this all over again, 8, and 56, 4, 5, and then 35, and 50, which was 7, and 49, and now we're back to the 1, okay? And as soon as that happened, that next was going to be, it's going to be 1, oops, going to be 1, and then it's going to be 4 again, okay? Because as soon as we see that remainder return, okay, and we saw the remainder of 3 actually return down there somewhere. Let's see if we can find it over here. Yeah, where we did it. Well, actually, it was this 1, because that 1 over here repeated over here. But we can see the 3, just to be sure. We see that 3. 3 down here. That repeated. Okay? right there. And you can see the remainder is always, it's either a 2, it's a 6, it's a 4, it's a 5, it's a 1, it's a 3, all right? It's pretty much everyone, 1, 2, 3, 4, 5, 6. Okay, it ran the gamut of remainders, okay? So that's how I explained that. Whether you wrote that down or not really does not concern me. It's interesting. It's an interesting fact. It helps when you have a decimal such as 1/7 and what that puts out, and that you could actually say, hey, it is time to stop. As soon as I see this repeating here, or I see my remainder repeating, I know I can stop. Okay.
Okay.
All right, now example 6. It's our favorite thing, using rational number conversions in problem solving. Okay, which is again my favorite thing. Brings things back to real life. Okay, so here we go. Eric and 4 of his friends are taking a trip across the New York State Thruway. They decide to split the cost of tolls equally. If the total cost of tolls is $8, how much will each person have to pay? So, of course, this idea of each tells us we are doing division. Alrighty, and what do we divide by what? Well, how many friends are there? Okay, if you said 4, I'm sorry, that's not right, because we can't forget Eric. Okay, again, another tip in reading problems, just be sure. You see this number 4 right here, but again, you have to understand that Eric is also included. So we have 5. We have five people, 5 friends, and we have $8. Okay, and $8. So we need to find out how much each person will pay. So we need to divide that 8 by 5, each person, because we want to split that $8 up into 5 for 5 people. So again, we just go through the motions here. We know we have actually a whole right there. That's one whole dollar there, and that's 5, 3. Oh, that was pretty quick, huh? That's 6. All right. So again, we're talking dollars and cents now. It's not enough to go, yeah, they're gonna pay $1.06. Okay, we know we're talking dollars and cents. Very, very particular. We need up to the cent spot. All right, so we have $1.60. So each person will have to pay $1.60. Okay, so this letter B here, can't see it very well on my screen here, but you have it right on your page as well. But it says, just before leaving the trip, 2 of Eric's friends have a family emergency and cannot go. What is each person's share of the $8 tolls now? Okay, so we had 5 friends, now we have 3 friends only. Okay, so same idea here, is we're going to divide 8 by 3. That's 2. And let's see, 2 and 6. Oops, 6 is always a funky one. 180. Oopsie daisy. I'm seeing something repeat here. I got that 20 right here, and I see that 20 again. Okay, so yes, indeed, this is going to repeat. Okay, now if we want to if we want to get this $8, it's something very important when you're solving a problem like this, because you might want to say $2.60 because the 6 repeats. But let's see what happens when we do 260 each times the 3. We end up with $7.80. We are 20 cents short, okay? Because $8 is what we're trying to get to. All right. Okay, let's go ahead and then, say $2.66. 266 times 3. Now we have, what do we have? 798. Okay, 798. That's not enough either. That's still 2 cents shy. So, truth is, somebody's got to pay an extra couple of cents. If you're going to put it into a pot, you would maybe go up to $2.67 each, which is going to give you, what, $8.01. Okay, somebody can party with that 1 cent. Anyway, again, when you're thinking about when you're solving problems, just make sure to check. I mean, it was $8 they needed to cover. You need to provide an answer that is going to cover that $8. So you could have said $2.66 for Eric's two friends, and he paid an extra 2 cents, so he paid $2.68 or something creative like that. Okay. All right, we are only 35 minutes into this one, and we are at the lesson summary, which I know excites everyone, including me. Okay. Our lesson summary here, the real world, yes, the real world that we live in, requires that we represent rational numbers in different ways, depending on the context, there's that word context again, of the situation. All rational numbers can be represented as either terminating decimals or repeating decimals using the long division algorithm. We represent repeating decimals by placing a bar over the shortest sequence of repeating digits. And I want to see you doing that on a consistent basis, okay, on a consistent basis. Alrighty? Well, good luck with your exit ticket and your problem set, and see you down the road, partner.